Now, could galaxies type change in time? Certainly, computer simulations show a galaxy's shape can change dramatically during a close encounter or a collision with another galaxy. This computer simulation shows two spiral galaxies that collide, and as they go through each other, we get the galaxies that throw off arms and eventually become an elliptical. We actually see in space something that looks exactly like what we saw in this computer simulation. These are two galaxies that are in the act of colliding. Now, in a collision between galaxies, individual stars are fairly much left unharmed. Remember, most of the space is empty, so they pretty much move right through each other. However, any gas or dust clouds, as they go through each other, they will have all of a sudden enough density to collapse in, and we get a burst of star formation. A small galaxy may alter the stellar orbits of a large galaxy to create something called a ring galaxy. Evidence, faint shell-like rings and dense clumps of stars of spirals colliding and merging form ellipticals. So ring galaxies are probably formed as two galaxies collide. This picture is of the Cartwheel galaxy. It's 500 million light years away from the Milky Way galaxy. It has a center elliptical galaxy with spokes with a ring of material around the outside. It's not unique. We see other ring galaxies out there. This ring galaxy, we're seeing the elliptical center and the ring on the side. Here we have a very nice ring with a center elliptical in the middle. So there's evidence for galaxy type change via collisions and merger over time. On a large scale, small galaxies may be captured and absorbed by large galaxies in a process called galactic cannibalism. It explains abnormally large ellipticals in the center of some galaxy clusters. The Milky Way actually appears to be swallowing the Magellanic Clouds, while Andromeda shows rings and star clumps of swallowed galaxies from the past. And if we look at very distant clusters, they have a higher proportion of spirals than near clusters. Distant clusters contain more galaxies within a given volume. So distant galaxies show more signs of disturbance by neighboring galaxies, odd shapes, bent arms, twisted disks, what astronomers call harassment. So now let's talk about distances to galaxies. The typical distances are measured in megaparsecs, or millions of parsecs. The nearest major galaxy is the Andromeda galaxy. It's 670 kiloparsecs away, or about 2 million light years. So any of the light we see from the Andromeda galaxy is light that came off of their stars 2 million years ago. The farthest known galaxies are about 4,000 megaparsecs, or about 14 billion light years away, and they're really just faint spots of light. Now, galaxies are too far away to employ parallax techniques, so instead we use the method of standard candles. The standard candles are usually Cepheid variable stars, or supergiant stars, planetary nebulas, supernovas, etc. So by looking at a Cepheid in another galaxy, we know from its rate of pulse exactly what its brightness is, and we compare that with something, say even in our own Milky Way with a known distance, and we can use the same inverse square law, standard candles methods to figure out the distance to that far galaxy. Now, in 1911, Hubble discovered that all galaxies, with just a few exceptions, are moving away from the Milky Way. And Edwin Hubble found that these radial speeds, which just means coming towards us or away from us, calculated by a Doppler shift analysis, which we call recessional velocity, and that recessional velocity increases with a galaxy's distance from us. From a plot of several galaxies' known recessional velocities and their distances, Hubble discovered a simple formula, that the velocity is equal to the Hubble constant times the distance it is away. Today, that expression is called Hubble's law, and the slope of this line, or h, is called the Hubble constant. Now, it's not completely agreed upon. These measurements are very difficult to do, but it's about 72 kilometers per second per megaparsec. So, with h known, one can turn this around and determine the galaxy's unknown distance by measuring its recessional velocity and using h. So now all we need to know is how fast it's moving away from us, and we can do that using redshift. We can figure out exactly how far away it is. Now, Hubble's law is the only method that there is for most of the galaxies in the universe. Now later we're going to talk about cosmology, or the study of the cosmos as a whole, and we'll discuss the implications of Hubble's law on the universe. Now there's some other methods we have for determining distances. One is the image graininess. The smoother the distribution of stars in a galaxy, the further away it is. Or the Tully-Fisher method, which says the higher the rotational speed of the galaxy, the more luminous it is. And the interrelationship of all these distant measuring techniques is called the distance ladder. So now that we have a way of measuring how far away something is, we can use its angular width in the sky to determine the diameter of the galaxy. So if we know then its angular width on a telescope, and we know its distance, we can solve for little d, the diameter of the galaxy. Now the main way of determining the mass of a galaxy is to do more or less what we did with our own galaxy. We measure the orbits of stars and use Kepler's laws. Now, galaxies rotate far too slowly for us to see any actual motions, but what we can do is measure the Doppler shift of the stars at different distances from the center of the galaxy. This actually tells us how the mass is distributed in a galaxy. And the total masses are about up to 10 to the 13th times the mass of the Sun, or 10 trillion solar masses. But there are a lot of smaller ones, down to just 10 to the 8th solar masses. Now when we study these rotation curves of spiral galaxies, we often get a strange result. There seems to be extra mass that is not producing light than we'd expect if the matter were all in the form of normal stars. We call that extra mass dark matter. This is a major mystery in astronomy right now. And there are signs that there are actually 3 to 10 times more dark matter than regular matter in galaxies. Later, we're going to talk about a couple more bits of evidence for dark matter. Now again, dark matter is not some exotic, strange thing. It's just something out there that doesn't shine light. That's why we call it dark. Most of the mass that we see is due to stars which shine light. We just can't see this dark matter. We know it's there because of its gravitational pull.